I'm Aras with a really unspellable last name. And I do the graphics programming at Unity Technologies and do the shader stuff and everything that's related to that. So my talk is going to be on shading and shadows, but actually most of it will just be on shading, because the shadows, there's not much to say. You either have them or not. So let's go. Now, how many of you actually know some shaders or know CG or GLSL or something like that? Oh, that's quite good. Okay, so for you, this will be not breaking news, but I find it that most of the people, they just don't have any imagination of what the shader is. Now, which of those images actually uses any shaders at all? There's one that is bright red, really fancy head, and the other one that is using some sort of, probably using some sort of skin shading thing. What actually happens is that both of them use shaders. One is a really complex one, which just always sets red. And the other one, it computes some sort of dot products between the normals and the view directions and computes some sort of rim lighting and diffuse lighting and takes the texture and produces something that looks like a human head. Some of the things that people think that are done by shaders are not actually done by shaders at all. For example, blurring the screen, that's not a shader. That's actually some more involved process that happens to use shaders for some of its steps. All a shader does itself is it operates on a single vertex or single pixel at a time. So that means you can't know your scene in a shader. You can't know which object it is rendered on. You can't know what are the close objects. You don't know which triangle it runs on. And you don't know which vertices it are neighboring to the current vertex and so on. All you get is vertex data like a position and normal in, and you output position and probably UV coordinates out. So you can move the position, for example, along the normal to extrude something, but you can't average the normals to round the object in fancy way. Similarly, for a pixel shader, all it does is renders single pixel. So to make something like blur, you can't do that just in a shader, because blur is by definition averaging multiple pixels together to produce something like blur. Oh, already said that. So if you use just a shader, you basically often can't do real interesting effects. You can add two textures together to do I don't know, detail texture. You can multiply two textures together, or you can raise texture color to a power of 3 if that gives you anything interesting. So back to my blur example. Who does the blur? It's shaders plus some data for the shaders plus some scripts that drive the shaders. And in this case, blur doesn't actually use lights, but most often you'll have some lights in your scene which provides some information for the shader. And often you can't just drop in the shader and in your project and be done with it, because a shader might require some more additional data. For example, the built-in bump mapping shaders, they need to have a bump map to actually look good. Or the specular shaders, they need a gloss map to indicate which parts of the object are actually shiny and which parts are not. Your custom shader might need ambient occlusion somewhere, like in vertex colors or a texture. Some of the shaders might need scripts that drive them, that change the textures or change the matrices or change the vectors for the shader and so on. Some of the shaders might need render textures to store intermediate results, like a blur shader. Back to my fancy blur example, what it does is render scene into a render texture. Then it happens to use a simple shader that averages neighboring pixels together. And then it repeats that same result until the scene is blurry enough. So the key here is actually the render texture. And the shader is actually a very simple one that just reads 4 pixels and outputs 1 pixel. Now, I'm going to show you some examples of what custom shaders could do for your game. One example, the water shorelines in the new 2.0 island demo. How did we do that? It's basically no complex shaders, none at all. Just some textures and some scripts that animate this shoreline texture. All the shader itself does is it has the wave mask texture and the wave color texture, and there's a script that actually does the voodoo thing. It scrolls the textures based on time back and forth, and it speeds them up and slows them down. And all the shader gets is the scrolling UVs on the mesh. Next example is cube maps for the reflections or cube maps for the lighting. Now a cube map is just like a texture wrapped onto a cube. It's kind of a skybox. A skybox basically defines the surrounding of the scene. And a cube map also, it's just like 6 textures basically put on the cube. Now, what a cube map can do is it can provide cheap reflections. If you just imagine if I'd have 6 textures representing this room into 6 sides, up, down, left, right, and so on, I could just say, okay, here's how my reflection looks in this direction. I see David here. And a cube map can also do cheap lighting, which can look good and can be very cheap to render. We had, even in Unity 1.0, we had reflective shaders, but we didn't find that many people using them. And I guess the most important reason is that it's really hard to do cube maps, because you have to do 6 textures that somehow represent your scene in 6 directions. You have to make them stitch properly on a cube. So what you would do is probably have your scene somewhere in Maya or in 3D Studio Max, set up 6 cameras looking up, left, up, down, left, right, and so on. Render these, how the scene looks like. Take these textures into Unity, and then you could use a reflective shader. Now, in Unity 2.0, we have a really simple API. We can just say, camera, render into cube map. And it will render into 6 directions, and you'll get the cube map back. So if you assemble your scene in Unity, you can just say, okay, from this point, I want the cube map. And whenever some object will be at this point, you can just use a reflective shader, and it will sort of reflect the scene. I'm going to switch to Unity now. Here's the fancy scene with the head in the skybox. Now, if I want this head to be reflective for whatever reason, and for example reflect the palms, in 2.0, among the scripting API examples, we have the complete wizard. If you go to camera, render to cube map, there's a complete working wizard, which I'm going to run right here. All I do is drag in the position from where it should render the cube map, and drag in the cube map itself, and hit render. Oh, it's a bit too small. And there's my cube map coming out of it. Now if you just switch get shader to some reflective one, and assign the cube map, where is it? There's my Silver Surfer. And of course, in your real game, you wouldn't have just a head in the skybox and a couple of palms around it. You can have that, of course, if you want to. But it's perfect thing for most of the racing games, for example. You have a shiny, bright car that should reflect your buildings and bridges and whatever. And you have your racetrack, so you compute 10 or 20 cube maps along this racetrack. Then whenever a car goes along the track, you just pick the closest one and use a reflective shader for that. So it's like, and because all the cube map here is pre-computed, so it's really cheap to render. Of course, we also have the ability to real-time update the cube maps, and so if you want the real actual next-gen thing, you can do that, but it's going to be a bit slower. The other thing that can be achieved with cube maps is cube map lighting. And right now, I didn't have time to build a proper head in the palm scene for the to show off cube map lighting, but what it can do is, in the cube map, you can basically encode lots and lots of lights, and then it's very cheap to render, and it looks very good. For example, this sphere here, it actually uses no lights at all. All it uses is two cube maps, one for the reflective thing and for the specular reflection, and the other for the sort of diffuse lighting. And often, especially in outdoor games where you have like in not very bright sunlight, but something like overcast sky, which basically illuminates your scene from all the directions, you could just compute a cube map from something like 100 or so lights, and then just use that. It looks better, it works a lot faster, because you don't actually have to compute lighting from 100 lights, just use one cube map. And for example, it was the lighting model used in Global Conflicts Palestine. They didn't use Unity lights at all. All they did was use a bunch of cube maps for different times of the day, and it works great. And for example, the same shader, if you just change the cube map, it can magically turn into a tuned lighting shader. It's all the same computation, it's just a different cube map. And just something we came up with Flashbang Studio guys yesterday. Into Zero, we have cube map set pixel. So if you have your funky lighting model that computes whatever dot products raises to some really funky powers, and you don't have to do that in a pixel shader, provided that your lights or whatever directions you use for lighting don't move. You can just compute a cube map and then, I don't know, look up that by vertex normal or something. And it's going to be a lot faster, and it's not that hard to do. If you want any example of how to actually do that, just ask me sometime later. One more example, something like skin shading. We don't have a built-in shader for skin in Unity, at least now we don't. But it can be used to great effect on your characters, and it can look much more interesting than just using diffuse, which sort of looks meh. We'll provide some sort of example project with all these shaders and cube map lighting and cube map reflections after the conference. So just ask us, and we'll hopefully do it. Okay, the last part from my talk is shader performance. Now, why would it matter, and what can you do about it, and does it matter at all? There's several ingredients to shader performance, and what games are most often limited by is something called fill rate. Fill rate is basically stuff that has to be done by drawing pixels on screen. And there's a lot of pixels to render, because like something like 1000 by 1000 resolution is 1,000,000 pixels to render. If you want to render that at 30 frames per second, there's 30 million pixels that have to be somehow computed. And that's assuming you have no overdraw at all. And in a game, you typically have like, I don't know, each pixel is actually rendered 5 times or so. So that's a lot of computations that need to be performed. And I'll talk about fill rate just in a second. And there's also like how many polygons and vertices have to be displayed, but that's often not the performance bottleneck unless you're running on something called the Intel card. And Joachim talked about that yesterday. Also shadows, even though they are cool, they can eat a lot of performance. So don't use them if you don't have to. Now, fill rate is drawing pixels, and it computes both the video memory bandwidth, because it needs to read textures and it needs to write the pixels back into memory, and it also has to perform some shader computations. For example, something like diffuse shader, for each pixel drawn, it computes a dot product from the vertex normal and the light direction, and then that is the diffuse lighting, multiplies by the light color, multiplies by the texture. And if it's a specular shader, it also computes the specular color. And if it's a bump map shader, it computes the bump mapping thing, and so on and so on. And fortunately, testing whether your game is limited by fill rate is really easy. Just change resolution, and if a frame count changes, that means what your game is limited by is drawing pixels on screen. And in real world, the difference between high-end graphics cards and low-end graphics cards, how much fill rate do they have is actually, the difference is very large. Something like a high-end GeForce card is like 30 times, it can draw 30 times as many pixels per second as a low-end Intel integrated card. And it also has like 10 times more memory bandwidth than the low-end card. So what do you do on low-end cards is basically you don't use high resolutions. There's probably no reason why your next-gen shooter game would need to run at 1600 by 1200 on an Intel card. Just say, okay, Intel card, 800 by 600, something like that. Or just, I don't know, educate the user or something like that. And of course, you try to reduce the pixel light count, because each pixel light draws the object additional time. So that means it's both some tax on the CPU, because it has to do additional draw call, and it consumes the fill rate because the pixels need to be drawn again for the slide. So low-end card, use no bump mapping, no pixel lights, just vertex lighting, limit the resolution, don't use full screen anti-aliasing, and you'll be fine, I guess. Similar thing goes for shadows. Shadows, they are sort of cool, but they eat a lot of performance. If you have played with shadows in 2.0 alpha or something, you might have noticed that. So if you use static lights or use static geometry, don't use shadows at all. Compute the light map, and that will be faster, will look better, and only use shadows where you actually have to, where you have like moving lights around, rockets flying around or something. And maybe even then you don't actually need shadows, because no one is going to notice that or something. And in particular, it's really helpful to think about point light shadows as being really evil thing. Because internally they use cube maps, where they have to basically draw the scene into all 6 faces of the cube map. So that's almost 6 times to render everything that this light can shine on. And then it uses this cube map to actually compute the shadows. So they are like really, really expensive stuff. Next, if you're writing custom shaders, what is the good performance? Like if you write your own shader, is it fast? Is it slow? It can be hard to figure it out. For example, this is some small snippet of CG code for a fragment program that does something. Now it reads the cube map from the input normal or something. And you might wonder, is this an expensive shader or not? Well, in this case, it's a really cheap shader. And one trick you could do is look up the shader in Unity's inspector, where it displays long list of cryptic things, basically of how the shader looks when it's actually compiled into shader assembly code. And among these cryptic things, you can find like, okay, this is whatever, compiled for OpenGL, it uses one texture or something, but it says one instruction, one text to read. And that's like about the cheapest shader there could ever be. It's like one instruction for the graphics card to perform. And for example, the built-in shader, something like a diffuse shader, it uses about 10 instructions depending on the light type. And something like a bumped parallax specular thing, it's probably, I don't remember exact counts, but it's like 50 instructions or so. So it's like 5 times slower. It's not exactly like that because the hardware is a bit more complex, but it helps to think as like a 50 instruction shader running 5 times slower as a 10 instruction shader. So that means if you have a 10 instruction shader, you can, for the same performance, you can draw 5 times more pixels with it. Which means you can have higher screen resolution, or you can have more pixelites or whatever. And the basic thing when optimizing the shaders is don't compute the stuff that you don't have to. For example, if you're computing, I don't know, camera's view direction, do something with the light direction. That doesn't actually change for each pixel rendered, because for each pixel that is rendered, camera still is looking in the same direction and the light is shining in the same direction. So you compute that somewhere in your script, call shader set vector, shader set color or something on the shader, and then you don't have to repeat the same computation all for each pixel that is displayed. And often complex computations can be just encoded somehow into textures or cube maps. For example, the X-ray shader on the wiki that Patrick did, all it does is compute the sort of angle between the vertex normal and the view direction, and then it doesn't actually output that as a color. It looks up the texture ramp of what color should it do. Now, if you would try to do the same by just computing the color in the shader, that might look very complex, because the color fall off you might want might be just some funky function stuff or not a function at all. And the shader is very cheap to render, and it's very artist friendly because the artist can just tweak the texture to achieve the effect he wants. And for example, these fancy heads here, it's exactly the same shader, just different textures. And that's about it. I think now I have the shortest talk ever, right? Any questions? Yep.
For the generated cube map, the rendered cube map, can you get those textures out into like Photoshop or something to manipulate them?
You could. I mean, we have a cube map get pixel, which is sort of slow, but you don't need that to be very fast. So you could read those pixels into a real texture and then call texture encode to PNG. And then you have your PNG file, and then you can...
They don't show up in your scene, though, in a little folder or something somewhere?
No, they're not like real actual texture files. They're some binary data that Unity happens to use, but it's possible to do. Yep.
Are there any constraints about the image that you bring in terms of is it 512, or is there when you bring in any kind of map, are there any limitations the resolution?
No, not really. I mean, there's limit that the graphics card can do. And most common graphics cards, they support textures up to 2048 size. But I mean, a larger image will consume more memory. It won't be actually that much slower to render. It would just consume more memory. I mean, if you're doing some high-end game and you don't care about your data size and something, sure.
Will it impact if you go online, like when you do it on the web? Will it impact the quality later on? Because, yeah. Okay.
Well, either I explained everything very well, or you didn't understand a thing. Yep.
So this means that get pixel to cube map, or cube map get pixel, is that then executed at runtime? Because you said it doesn't actually really bake out it.
No, I mean, in the context where you want to render the cube map and you want to get the texture back to manipulate that in Photoshop, then that means it doesn't have to be in the game. It's just probably some editor script that you just compute the cube map and then tweak it in Photoshop, save it, and build that in your game. Of course, if you're calling cube map get pixel in your game for whatever reason, then it's all, of course, it's executed in your game. But probably, I don't know, maybe there is a reason to get pixels from a cube map in the game to I don't know, compute the damage or something.
It could be a way of saving on download size, I suppose.
Yeah, I guess so. Yeah, I mean, just try it and see if it's too slow for you. We'll optimize it or provide something else. Yep.
Showing how you had Unity generate the Q map again, the wizard.
Yep. Oh, it was. Where's my script? All I have here is a script that generates this cube map. It renders from some transform you indicate into the cube map you indicate. And this very script is actually just in the documentation of Unity that you can get. This camera rendered a cube map, and it's exactly the same script here that shows how to do it in the editor using a wizard, or how to do it at runtime if you want totally dynamic reflections. So, I mean, here I have my head. I will create some, oh, not here. Some fancy spheres. Render the cube map again. And there I have my spheres reflecting from my silver surfer head.
Basically, anything you add on has to be read.
I mean, if you're using this thing that computes the static cube map, then of course it needs to be recomputed whenever you change something. But you can also just use a render texture cube map and just live update it at runtime, which is going to be way more expensive. But if that's what you need to do, then that's what you need to do. Yep.
You had mentioned that you use cube mapping extensively in global conflicts, Palestine. Can you tell us how you actually applied it and why it was effective as it was?
I guess actually Nicholas knows a lot more about it. If you can come in.
I can. Just the question again. We just heard global conflicts, Palestine, and then I missed it.
Oh, so Aras was saying that he had used cube mapping within global conflicts, Palestine, and it actually saved a lot of overhead. How exactly did you use it, and why did it? How did you apply it, and why was it so effective in that application?
Basically, that is an outdoor game where we don't do any dynamic street lights or anything. So we have sort of light map on the ground, so you get building shadows, and then we just have the sun and lots of skylight. So it means that basically means there's no the lighting is the same all over the level. So yeah, so it was just okay. So I want to pre-compute this. It was also that on a lot of the images we saw from that region, actually it seemed like there was that we had some very soft lighting. So I found maybe some dust in there. I'm not quite sure what it was. So I want to capture this, and basically we wanted this to run on any card. We're talking about way before GME. So basically, so what we did, we just have these cube maps. We have for each different lighting, we have 3 cube maps. We have a diffuse cube map and a specular cube map and a skin cube map, which does sort of reddening of the skin kind of thing. And basically what we just did was just that, yeah, we had sort of sample scenes where we had a sphere, where we had spheres set up, 3 spheres, and then we sort of had a small script that did render to cube map on each of these spheres, and yeah, we sort of basically like the wizard just running automatically. And then we could just sort of adjust a lot of directional lights, sort of just move them in relation to the cube maps or to these spheres, and then one would have a diffuse shader, the other would have a specular shader, and the last one would have a skin shader. And so, I mean, so then we just save them out into assets, and then we could just pull them into the main, and we just use the main scene. So that's basically how we sort of set them up. And we had a bunch of custom shaders that sort of, instead of doing lighting, just use cube map lighting. Yeah, I mean, I assume we'll be shipping some of these after the conference with the notes of as a few example ones. And that's how we applied them.
But you didn't actually apply cube maps to spheres within the game. You did that as experimentation. How did they work within the game?
What we did was we had some spheres set up, which we used to render the cube maps. So we just had these spheres. So it was like, okay, this is like just like basically like you have these spherical lighting things that people use when they're sort of measuring light. And so we baked the cube maps from those, and then we applied it to all in-game models.
I guess the reason why it's fast is that because essentially no lighting has to be computed at runtime. So it captures the complex lighting from the whole sky, and it does that in one pass by just using 2 cube maps or 3 cube maps or something.
Do you use those for, say, reflections in windows as you walked past something? You could actually have that particular cube map pre-rendered so that you didn't.
We could do, but we didn't, because this was how to be a low-end game. And I mean, and basically for Windows, I mean, the problem with the cube maps is that they don't really change as you move about. It's like everything infinitely far away. So for Windows interface, you sort of got to ask yourself, okay, how many different cube maps do we want? So if we want sort of the proper reflection in each of these windows, that's just not going to work. So much better to use planar reflection for that. And in our case, we just, I think for the next game after I left, they had another cube. They had sort of another cube map they used, which is just sort of a cube map rendered from a generic place in their town. And that was just fine.